From Stanford University, but before we start, this is an awarded paper with an honorable mention, I believe. And so here you go.
Thank you.
And let's give a hand to Evan for their award publication, and to Maneesh and to Sean. All right, and Evan is going to talk about Scanalog, and we're now diving a little deeper into creating analog circuits with FPGAs.
All right, hi. My name is Evan Strasnick, and of course this work, I'll say, would not have been possible without my mentors at Stanford, Maneesh Agrawala and Sean Follmer. So suppose we want to make a proximity sensor. And specifically, let's just make an LED light up whenever we cover this infrared photoreflector. Analog electronics are a part of any system like this that has to sense or act on signals from the real world. So this photoreflector outputs a weak signal that looks like this as my finger begins to approach the top. But what I want is something more like this. Sharp transition, a full swing in voltage from low to high. And we call it conditioning whenever we clean or amplify a sensor in this way. And this sensor is just one type of thousands that we would need to condition like this. This analog circuit that we'd need here is a fairly simple one, but it can still be tremendously challenging to design. In general, unlike digital electronics, for which we have robust microcontrollers and high-level libraries and amazing tools like we've seen so far in this session, the processes of designing and debugging and prototyping with analog electronics remain particularly difficult for a number of reasons. So first of all, analog circuits are, or analog design rather, is very slow and error-prone. So manually prototyping will limit our ability to rapidly iterate on a design. And we know that it often results in bugs such as miswirings. So here I'm going to build the circuit that will light our LED, and you'll see that I myself actually make a genuine wiring mistake in doing so. Analog circuits also suffer from issues of noise. So here, hopefully those of you in the back will be able to see, as we move this sensor and just point it in different directions, the signal is moving slightly up and down on our oscilloscope, and that's just noise due to background radiation. Encapsulation is also particularly difficult in analog design, and what I mean by that is that changes to one part of a circuit will affect all the other subcircuits throughout. So here I just add a motor on the same power lines as our circuit, and we can see how signals from our sensing circuit will change dramatically as I just turn the motor on and off. And finally, debugging is hindered by our limited ability to perceive the internal state of the circuit. So typically we will manually probe points across the circuit with an oscilloscope, as I do here, to try to understand behavior or to isolate a bug. So these fundamental challenges in designing and debugging analog circuits really boil down to obstacles to our understanding and iteration. What we need is a way to iterate faster, that is, to avoid manually adjusting or simulating the circuits. And we need a way to understand what's going on inside the circuit as we design. We think there's a technology that we can leverage to address these difficulties. The field programmable analog array is a chip that contains analog components that we can programmatically connect together in different ways to create different circuits. It's essentially the analog cousin of the FPGA, if you know what that is. And instead of exposing low-level control of individual analog components, it allows for users to design with high-level functional transformations or modules, such as adding a low-pass filter or a summing stage. And while programmatically designing with real signals is incredibly powerful, existing design tools for FPGAs don't really leverage this capability to assist designers in rapidly exploring their options or in debugging their issues. So our goal is to augment this platform with the tools to make changes in real time and to understand their effects. So our contribution is Scanalog. It's a hardware and software platform that builds on top of this FPGA to improve the design and debugging of analog circuits. The hardware consists of three primary components: the FPGA, a digital oscilloscope which can measure signals, and an arbitrary waveform generator which is capable of synthesizing signals. So we're now going to build the conditioning circuit for that proximity sensor I showed earlier using Scanalog's graphical user interface, which communicates with our instrumented FPGA. So to begin, I first just connect the output of our sensor into one of the inputs of the PAA. As we open the Scanalog interface, we see several panels. So the user builds their circuit in the workspace and adds modules from a palette just beneath. Tests and assertions can be added from the next panel, and the following section controls visualization settings and provides a detailed view for manual probing of signals at high resolution. An optional command line can be used as an alternative to the GUI. So in Scanalog, live signals within the hardware are measured and visualized alongside their components in the graphical interface. So as I first cover the sensor, note how we can see the signal move up and down slightly in real time. Now, before I build this circuit, I'm going to want to make it easy for myself to iterate, without having to do this covering of the sensor with my finger 1,000 times as I design. So I can actually tell Scanalog to record a few of these examples as I touch the sensor. Then, I can have Scanalog play back one of those signals from input 2 now on a loop. So here, after I click, the same signal that I've generated is now being synthesized and played back into the hardware, allowing me to test reliably on this input as I go. However, the signal is too small right now to be useful, and it may be small enough that you can't see it, so I first need to add a gain stage. Scanalog allows users to quickly add high-level modular components and directly manipulate their parameters while observing their output. So here, as I adjust the value of this gain parameter, we can see in real time how the signal changes. And I should emphasize that nothing here is being simulated. So we're reconfiguring the hardware and displaying the internal signals that we read in real time. Our next step is to threshold the signal at a given voltage. We want a digital high when the sensor is covered and a low otherwise. So this is the job of the comparator module. So I'll add one and I'll set an initial reference voltage. Now we can not only tune the parameters of the comparator to change the output, but we can also change the parameters of the gain stage before it. Scanalog visualizes the signal at all points in the circuit at once, so as we make changes to one module, we can see how it affects the behaviors of all the others. By interactively tuning and observing the signal, we can quickly arrive at exactly the behavior that we want. As I tune the parameters, I want to make sure that I don't introduce any new bugs. So Scanalog also implements assertions for analog circuits. We can add these assertions directly into the workspace at the output of any module, and much like assertions in software development, they'll alert us in real time if any invariant is ever violated. So here I add a test that will alert me if I've made the signal too large for the voltage range of the board through my gain. If we set this gain too high now, the assertion alerts us to the potential issue. Users can actually write their own assertions to create arbitrary tests. And finally, we can now test the circuit that we've built. So as I cover the sensor now, the output of our comparator goes fully high, and that's what we wanted. This is actually now functional hardware that Scanalog was producing as we designed. So in fact, we can just disconnect the board and embed it directly into our application if we want. And just to show that that works, if I plug in Scanalog's output into the LED circuit from before, it works as expected. So as we've seen, Scanalog improved our iteration by allowing us to make changes to hardware in real time, and it improved our understanding with live visualizations and helpful debugging tools. Obviously, the design of Scanalog was based off of a number of tools, such as those that we've seen earlier in this session and previously. Toastboard now, which you've seen twice already, is a recent debugging and prototyping tool that provides helpful means of detecting and resolving bugs. Scanalog achieves the same goal for analog circuits, but differs in a number of ways. Most importantly, users don't need to manually construct the circuit themselves, which allows them to iterate much more quickly and with less error. We also take a great deal of inspiration from an interface by Brett Victor that imagined visualizing and manipulating different parts of the circuit in real time. So while powerful, obviously, this tool is just a simulation, while Scanalog realizes the same vision on actual hardware. So I'll give a brief overview of how we implement some of these core features. As we've seen, Scanalog has these three main hardware components: the FPAA, the digital oscilloscope, and the arbitrary waveform generator. Let's talk about how these components integrate to enable the features of Scanalog. As a user design interface, we correspondingly reconfigure the hardware in real time. Details on how we achieve this are in our paper, but in short, we translate each module in the interface into an equivalent subcircuit, and then we set memory values that we've reverse engineered in the FPAA to appropriately configure its analog components. As these changes are made, the system is also capturing data from an oscilloscope that reads internal points in the circuit and sends the data back to the interface to visualize the signal in real time. And finally, when the user triggers the replay of a signal, we program the lookup table of the arbitrary waveform generator to render that stored signal, and then we inject it back into the circuit through a dedicated input. How do we record and visualize live traces from each point in the working circuit? Because we use only a single oscilloscope, we employ time multiplexing to continually scan across the output of each module. So in practice, as the user edits, we are, under the hood, continually flashing additional updates to the FPAA that reconfigure a new connection between the output of the next module and the input of our oscilloscope. Once that reprogramming is complete, the oscilloscope captures a trace and sends it via USB to update the corresponding visualization. We actually get our name Scanalog from this scanning technique. And you'll observe then that as we increase the size of the circuit, the refresh rate on any one of these individual modules will decrease. In the paper, we discuss two ways to prioritize particular refresh rates, either by toggling live updates for the modules of interest, or by switching into a manual probing mode for sensitive applications, which provides a high refresh view on a single module. With traces captured for each module, we can then begin to implement debugging features like our assertions. So on each incoming update, the test logic of this assertion is run as a function over the sampled data points of the trace, reporting any issues in real time. We then expose the ability for users to write their own tests and assertions using JavaScript. So here we show how a typical test might be written for a set of voltage samples, that's that parameter data, and a module object M. In this test, we're simply iterating over the entire trace, and we report whether any voltage values were negative. Users can easily edit test skeletons to define arbitrarily sophisticated tests using a built-in editor right within our interface. And then we actually leverage our ability to reproduce recorded signals to also implement on-demand unit tests, much like we use in software development. So any recorded signal can be set as a test signal. And then with one click, unit tests will iterate through our set of test signals, letting each propagate through the current circuit and evaluating the result of all assertions, and then reporting the net results of these tests to the user. So here, as the first signal passes through the circuit, we see that the assertion is not violated, so the test will report a pass. However, for the next two signals, these tests will fail, and the unit tests will give us those results. So finally, I should reiterate that as the user designs in the Scanalog interface, they're in fact programming functional hardware that they can disconnect and put into their own application. However, if users wish to instead fabricate their circuit for cheaper or mass production, or even just share it, Scanalog can convert its internal representation to a standard circuit layout, which we can then import using fritzing or other PCB design tools. And now here's a few example circuits that we've created using Scanalog that will demonstrate its flexibility. So this first demonstration cascades a number of filtering and amplification stages to create a functional EKG. To create this, I simply placed electrodes over my chest and I plugged them right into the Scanalog hardware. And then I could easily subtract the signals and string together different conditioning modules, tuning them all in parallel to shape the signal. The assertions I placed also brought to my attention any issues that we might have, like we see here. And you can see the signal output from our EKG there at the bottom. Our second example shows how we can manipulate live audio signals, which are typically in analog format, to interactively mix and filter and crossfade music. So here we've connected to Scanalog's inputs the headphone jacks of two mobile devices, and we connected Scanalog's output to a speaker. And then by summing these two audio sources with adjustable gain on each, the user can fade in and out songs. I'll give a little demo of that now. So here's a first song that we want to mix.
To my surprise, discovered that I really don't know much of what I...
And we're going to mash it up with this song. And here's what it sounds like to play with that. And of course, because we can update our hardware in real time, we can use this reconfiguration for performance as well. So finally, we wanted to see how users could create circuits such as these. So we took this sensor conditioning application that we've been using as a running example so far, and we converted it into an informal design evaluation. We walked 8 users with basic circuit design experience through the Scanalog interface, and then we just gave them a sensor and told them to build a circuit that would transform the signal according to the output specification. All of our participants succeeded in building this circuit, and they reported in follow-up interviews that they most appreciated the ease of rapidly tuning modules and observing the changes through live visualization. One participant here expressed joy at not needing to manually probe across their circuit to isolate issues, saying conventionally you could build a whole circuit, and then when it didn't work, you'd have to test each part to figure out why. Another participant expressed feelings of immediacy through the use of Scanalog. The closer I can get to what's happening in the circuit, the easier it is for me to understand what's going on. So I'll close by summarizing what we hope to contribute through Scanalog. It supports the design and debugging of analog circuits by allowing users to tune functional hardware in real time using direct manipulation. They can simultaneously observe the effects of their changes through live visualization of internal signals. It brings helpful debugging features to the world of analog design that assist users in detecting, isolating, and resolving bugs. And finally, it allows users to record and replay signals for on-demand testing. In this way, we've been able to bring a number of powerful techniques from programming and digital design to the task of building analog hardware. Together, we hope that these tools allow users to gain a better understanding of their circuits as they design. But we think that there's more work still to be done here. And so we hope that others will continue similar work in this vein and to better support designers and creators. And I'll close with that and thank you all, and I will open the floor to questions if there's time.
Gerard Laput, Carnegie Mellon University. Hey. Great work, Evan. Can you elaborate a little bit on the record and replay part? Where is the signal being stored and how is that being played back? Maybe I missed it in the presentation.
Yeah, absolutely. So I didn't go too much into detail on this. So we are recording signals at all times, and the user can choose to connect directly to one of those signals and press a record button. Then that will store a table of recorded signals. When we replay the signal, there's a menu that pops up, and the user can select the signal that they want to replay. And so this is stored actually on the desktop interface, the GUI. And then we program the arbitrary waveform generator via USB. It's essentially, you give it a number of samples, and it interpolates along those samples and synthesizes that signal, which we then inject as an input into the board.
So, okay, great. So basically, recorded with a specific sampling rate and then stored into memory the actual ADC values and then playing that back with the same sampling rate.
Yeah, obviously in order to visualize any of these signals we have to digitize them and sample them. And then the arbitrary waveform generator, you give it a series of sampled points and it does the interpolation. So there's a bit of lost precision there. And there's limitations on the maximum length of the signal and so on and so forth. But as just a useful tool, it really alleviates the need to regenerate a particular gesture or analog input, and just gives you this powerful way to reliably run tests or reproduce signals.
Great, thank you.
Mm-hmm.
Hey, Evan. Fantastic work. So I have a question. If I compare your visual language to other data flow programming languages, MaxMSP, PD, they tend to have two types of signals that flow through there. Whatever happens at audio rate or at full signal rate here, and then there are control channels too, which would correspond to the parameters that are inside your nodes. So those parameters, is it true that in the current version you can change them in the UI, but each time that generates a new configuration for the FPAA, right?
Yes.
So would it be possible or not to expose those parameters outside of the blocks and make them changeable at runtime? Like for the audio mixer, right? What I really wanted is two faders, so two pots that then flow into that as well. So I think could that work with the FPAA, and also could that work with generating non-FPAA low-cost hardware?
Yes, absolutely. So great question. The let's talk about the FPAA as it just is designed to be used by this, we're using a particular FPAA by this company. Most of these boards, you have a sort of proprietary software interface that you use to design. And in that way, what you're describing is not really possible. That is, you would have to understand how to program the FPAA on your own, as we've done here, to be able to take data that you read and then in runtime plug that in to change parameters of the circuit that you've built. This is possible because we've spent a lot of time reverse engineering this board, but in the implementation that I've shown you of Scanalog, we haven't built in that sort of control flow to take signals, do some sort of digital processing or mapping, and then return that into parameter space. But it's totally possible, and I like the suggestion, and I haven't really thought much about it, but I could very much see, using our capabilities to expose some visual language, allowing the users to say, I want to map any of these signals to a parameter in this way, and then just adding that control. So it's a really great idea, and I thank you for it.
Great, thank you.
Mm-hmm.
That was not a question. Fake news.